All right. Sorry about that. But anyway, yeah, it's recording now. As I was thinking, I thought, man, not hit that button. Okay. So let's go back to script. So hopefully that's it. I mean, if you understand that concept, this will be easy. So now, predict, we'll need to use that Gaussian function, which I think we had, yeah, the Gaussian function still needs to be defined over here, right? But it's basically just that equation. So now that you understand the logic, let's do the training function actually first. So let's go to train. So I'm going to create the train function. Okay, so define train for naive Bayes. This train, if we look at it at the bottom, takes X train and Y train. Okay, so then I'm going to put these here. So X train, Y train, colon. Okay, and now we're going to proceed to do basically that. So we need some information. So some easy things. So the number of samples and also the number of features. So n samples and n features. Okay, we're going to get those basically from the shape of X train, right? So the shape of X train should give us these parameters. So these parameters are basically what? 150 samples, right? 150 samples. And 4 features. So this is the data here. For features. So this will return then 150, comma 4. Okay. So that's the first thing we do, n samples and n features. Then we want the number of classes. So I'm going to do list of classes. Okay, list of classes. So we need from Y train the classes that we have in there. So a neat way of getting that is just to call the Numpy function unique. And what unique will do is that it will just give you the unique values. So you might have a million classes in there, but they're all 0, 1, and 2. So the unique values will be 0, 1, and 2. And this will return a list of the values. In our case, it'll return, actually, because we only have 2 classes, it will return 0, 1. Okay, and then we want to know actually, because that's a list, we actually want to know how many classes we have. So we can say n classes, which is just going to be the length of list of classes. Okay, that's it. So that's what you want to understand. The next thing we need to store the means and standard deviations for every feature for every class. So we discussed, this is an important thing to understand, okay? So let's see if we can go back to, this would be over here. Oops. All right, so if we scroll down, this was this last slide that I did on Monday, which basically said on the rows we have now the classes, right? So 0 and 1, 2 classes. And on the columns we have the features. So in our example, we have 4 features, F1, F2, F3, and F4, right? for every class, we need to calculate the mean for that feature, right? For each individual one. You guys see that? And then that way, once we have them, we'll be able, on a per class basis, to be able to predict if a given new test sample X, which has features F1, 2, 3, and 4, does that sample fall within that distribution or not by using the Gaussian function. And that's a nice way of knowing if the features that we're looking at are representative of that group. Okay. We're going to repeat the process for the variances or standard deviations. So again, on the rows, we need the number of classes. On the columns, we need the number of features, F1, 2, F3, F4. Then we slice from our data, class 1, class 2. And then for each, so when we do class 1 for that group, calculate the means and standard deviations and so on. So that's possibly the hardest part to understand of all of this. So if this makes sense, let's go now. And try to implement that. Okay. So to implement that, let's just say calculate mean variance for the Gaussian per class. Okay. So how do we do that? That's the question. First, let's create the objects that are going to store the data. So the arrays, right? So we need 2 arrays or 2 Numpy matrices of 2 by 4. One for the means, one for the variances. So let's create that. So I'm going to say, one for the means, one for the variances. So we can say means equal np dot zeros. And then it's going to be of size n classes, which is 2, comma, n features. And then we can say that the data type should be something like float. Okay. That's the means. Then we can do the variances. And this is also NumPy zeros. Again, of size n classes by features. Okay. And then the data type also. np.float. Okay. Same thing, only they're going to hold different values. But now we have what we need. And then if you remember, if we go back to the document, we're gonna go to this one. Right, and in this document, if you remember, the formula was this, right? This is the Gaussian function that we're using. But we also need, remember this last little term, the probability of the class itself, okay? So the probability, how many samples we saw of the class. And so we're gonna do that one as well, because if you remember, it's a sequence of multiplications, and then the last one is the class. So like this, right? The priori, as we called it. And so we also need something to hold that. There are only 2 classes. And, so really, see, we only need, since we only have 2 classes, we only need two values here. And we can just create an array to hold those two values, basically. So let's go back to the notebook. And we're going to create here a new one. Let's call it priori. Just keep in mind that's what holds the classes. So that's going to be np.zeros and n classes, comma, so size 2 basically, and then data type is going to be np.float. Okay, we can add a comment here at the end just to indicate this holds p c, the class, right? Probabilities of the class. Okay, in the formula. All right, now we have these parameters, and now we need to populate the means and the standard deviations. So what we can do is we need to do this on a per class basis. So we're going to need some kind of an iteration. So I'm going to use enumerate. So enumerate, remember, takes a list and returns two things. It returns the index and the value. In our case, the index and the value are probably the same. So like you can see, this is 0 and 1, and then this is 0 and 1. But it's still more convenient to do it like that. So for IDX, C as in class, in enumerate, and then we're going to enumerate list of classes. Just like that. You guys see that? Okay, and then now we can proceed to populate the values. The trick is, look at this is the tricky part. We have the entire data set, right? X train. So let's go back to the whiteboard. So we have the entire training set, X train. Okay, and the training set, it's bigger than this, but let's just say it's like 10 by 4, right? There's 4 here, F1, 2, F3, F4. And we have the labels. And I'm just to keep it convenient, I'm going to say 0, 0, 0, 0, and I'm going to use actually, I'm going to use 3 classes just for maximum effect. So 1, 1, 2, 2, 2, 2. Do you see that? So we need to calculate for every column, right? For every column, all 4 independently, the mean and the standard deviation. We need to find them. But it has to be per class. So what I need to do is every time I iterate through a class, I'm going to look at these values and I'm going to say, okay, the first class, which is 0. So when it equals 0, only give me that data. So what it's going to do is it's going to slice just this. And all the rest will be ignored for that first iteration. So now when I calculate means and standard deviations, I will only calculate it for this data. Do you see that? And that's how on a per class, I get the means and standard deviations for every feature. Got it? I do the second one, right? I do the next one. Now it's going to be classes 1. Okay, so I'm going to go ahead. When it equals 1, So it's only going to slice that data. You see that? It's only going to slice that. And so now, when I calculate the means and the standard deviations, I'm only calculating them for the class. So I'm only going to take the means and standard deviations from these. You see that? And keep in mind, there could be a 1 down here, right? And that one will also be grabbed. All the ones. I just did this like this for more convenience, but it'll grab all of them. And then finally, when you do the third one, same thing. Now we're going to iterate class 2 . We only slice the data that matches class 2, and out of that, we are going to calculate the mean and the standard deviation for that. And so we're going to store all this data, and that's why we need these, right? Because we're storing for every class the mean of that feature, the standard deviation of that feature. So that's what I'll be doing here. So now if I go to code, then hopefully it'll become more clear and obvious what I'm doing. So I'm enumerating, and now I need to take from X train, I need to slice out some data. So I'm going to say, only give me the samples in Y train that are equal to the class C. You see that? That basically takes all the values in Y train that are equal to that class, 0 or 1, right? And it returns the indices of them. And then once I have those indices, then I can slice only the indices in X train that match the condition. Did you guys understand this? This is probably the hardest part, I guess, of the code. Yeah. So as I said, it's the example I was discussing, right? X train contains the data. But I only want the X data per class. Now the classes are in Y train, right? And they align. X train and Y train have the exact same number of samples, right? So all I do is I look in Y train. I look in that vector, so I do this. I'm gonna look in, so I have the data like this, X and Y. I want this data, but the labels are here, right? And it's like 0, 0, 1, 1, 0, 1. I only want class equal 1. That's what I want. The indices here, I did 2, 4, 6, right? So 6. So it'd be 0, 1, 2, 3, 4, 5, right? That's the indices. So now I want to match it to class 1. Well, that's where I do that little trick where I said where Y train equals C. C is 1, so it's only going to match that, and that. You see that? And so this should return only the indices that I care to slice out of X train, which are 2, 3, and 5. You see that? So 2, 3, and 5 are the ones that are selected. Does this make sense, guys? So that's what I did, right? So I'm comparing Y to see that it matches a particular value C, 1 in this case. And it's going to basically then tell me, okay, those ones, those true ones are 2, 3, and 5 positions, those indices. And then now I'm going to grab 2, 3, and 5 because they belong to class 1. And from here, I'm going to calculate the mean and the variance for the 4 features, but just for 2, 3, and 5, because that's class 1. So that's exactly what I'm doing in that code that I showed you. So I do y train equals C. Now C is, we're enumerating among the classes, so it's a for loop. Because first we're going to do it for the 0 values, and then we're going to do it for the 1 values. You see that? It's a nice way of doing it because we could have 10 classes or something. And so now we have the data slice in there, and now we can call it XC because it's the X data, but now only for the particular class. Okay, only for the particular class. Once I have that, then should be straightforward. We want to calculate from XC we want to calculate the mean. And the only last thing that we have to tell it is on which axis, right? On which axis we calculate the mean. So we're going to say axis equal 0. Because it's going to be, we calculate this. So let's say that we've grabbed 2, 3, and 5, right? If we said calculate the means along the 1 axis, what would happen? We would calculate for this, this, and this, the mean. But that's not what we need. We need the mean for this, this, and this, 2, 3, and 5, because those are the samples, because this is feature 1, and we're doing it on a feature basis. Do you guys understand this part, guys? Making sense? So we're going to do 2, 3, and 5 along this axis here. So we need to say axis 0, whereas this would be axis 1. All right, so now I'm going to go ahead. And that's why this XC mean is axis 0, basically. Okay. All right, and so I have that mean, and then that mean now can be assigned into my means array over there. So I'm going to say means okay, and this is going to be for the first row, so IDX, right? Because this is class 0 and IDX is 0, and this, when it's class 1, this is 1. But they match here, but maybe they wouldn't match at another situation, right? So we just want to make sure that we put them in the right row. And then this is just all of them because we get 4 of them, right? So it'll just know that we get 4 over here. It'll map it to 4 because we have 4 in this. We defined it as 2 by 4. And so basically what that ends up happening with this line of code here is that I have assigned all these values. This first row is done. Okay. And now I'm going to do the standard deviations, which is exactly the same thing. It's exactly the same thing. I'm going to say from X C dot variance. Okay, and I'm also going to say along the same axis equal 0. So I'm going to do it along the same axis 0. And now I assign it to my variances matrix, which is this one above here. So it's going to be variances. And again, IDX, comma, all. So now that row is complete. And in fact, all the rows will be complete once you have done this. Okay, and then the final part is to calculate the priori, which is this, the classes. Okay, so I'm just going to do here priori. This is only two classes, right? So only two values need to be computed here. So we're going to say again, IDX, that's the index, and we assign to it now. So what do we need? We only need the number of samples per class. We actually have that here, right? XC, when we slice it for 1, we have the number of samples for 1. XC, when we slice it for 0, we have the number of samples for 0. So we can actually get that value from XC. So what I can do is I can do X underscore C dot shape 0. You understand? This is just getting, basically what that does is it's giving me, if I go back to the example, or on the whiteboard, I sliced 2, 3, and 5. So how many samples do I have? 3. So that's what I just got, 3. And then I had a total of 6 values. So it's going to be 3 divided by 6. You see that? That's the number of samples in that class. And so what I'm going to do now is take, so this is XC dot shape 0 divided by the length and samples. I had already calculated that parameter. Because it's a probability, we want to make it a float just in case. Right, like that. And then now we have, believe it or not, those are the parameters. We've got them. We've got the parameters. And so now we're just gonna return them. So we return from train, we want to return the list of classes, means, variances, and priori. And then just whenever we're calculating for a new sample, right, we just need to do it for all the classes and select the maximum one. So that's basically the idea. So we've got priori, means, variances, and list of classes. Okay, so that should be done. Believe it or not, the train function is done. We've got the parameters, and now we can go ahead and do a prediction. Notice that we haven't yet used the Gaussian function, right? The Gaussian function take these parameters. It'll take the mean and the variance to determine the distribution of the data and then see if a new sample belongs to that or not. You know, so that's the next step. So now that we know what the parameters are, actually, we can just change that parameters variable with these. So here, I'm going to send them now. And then here, I'm also going to send them now. And then in this predict, I'm going to send them. You see that? And let's see what else. Now, train returns now all of those instead of parameters. Okay. And here also. Now, you could have just left parameters and made it into like a quadruple, right? You know, tuple with 4 values. That's also something. Some people do that a lot, actually. So it's up to you, however you see it better. But now we have train should be done. And now we can focus on this one should also be done, right? Predict, set. So all that remains is to use the predict function, or to define, sorry, the predict function, which is this one. Any questions? Yeah. here. Oh, yes. Here, you mean. Thank you. Good. All right. So now we just do the predict function. And remember, for the predict function, we're going to need to use the Gaussian function. Okay, so we should probably try to define that one. And what is this Gaussian function? We're going to basically write a simplified version of this, okay, of that function. I'm sure there are also built-in Gaussian functions where you just plug in the parameters. That's a thing. But here, you know, we can just attempt at writing it, okay, at least a simplified version of it. But it's just what I want you to understand is that this function is basically this, okay? It'll take obviously variance, mean, and then it needs to take the x as well. And then it just outputs a probability between 0 and 1, saying if that current value belongs to that distribution or not, how likely it is. All right, so to do that then, let's go back to the code. And we need to define, so let's define Gaussian, which was up here. Okay, so the Gaussian will take, the Gaussian takes an index, let's say, it takes the x value, let's call it xs. That's the value that you're comparing to see if it belongs to the distribution or not. Then we can send the whole means and variances, and we'll need to select just the appropriate one for us. Okay, so we need let's think about this function. So this function has a numerator and a denominator. So let's say numerator divided by denominator. Okay. All right, then we need to define these two. Okay, so those are the two parameters that we also need to define. So we can think about it as yeah, so let's think this is the denominator, right? That's the denominator. So that is what? The square root of 2 times pi and this is the standard deviation actually. So variance is this squared, right? If you take the square root of something squared, it gives you the thing without the squaring, right? So that's why we can put this term inside. So it would be 2 pi, this thing squared inside the square root. You guys see that? So we can do that. And that's going to be our denominator. Okay, so that should be easy. So let's go here. And so the denominator we can do by writing np dot square root, right, of 2 times pi, which is numpy dot pi, times, and then the variance, right? Because the variance is squared version of standard deviation. So then variances is the matrix. And then from there, we have to select which one. Now remember, variances is a matrix of size 1 by 4, right? You guys agree with that? So it's 1 by 4. We're doing this. We're comparing one X sample, which has 4 features, right? So we need to compare it to all 4 features. So that's why what we're going to do is we just plug in IDX. What this does is that it gives us all 4 features. So it returns a vector of 4. not just one single value. Okay, so it's a vector of 4. And so these 2 times pi are multiplied times each one. Okay, so just keep that in mind. So that's where, you know, the power of NumPy comes in doing these vector operations. All right, and then in the numerator, then we would look at this part over here, right? But again, remember, x is a sample of 4 features, right? So it's a vector of 4. The mean is a sample. It's basically a mean of all the samples, but it's also of size 4. Okay, so we have those 4 means. So we're gonna do this operation as the numerator. So this is e to the x, where x is this thing here. Okay, so we need to do that part. Okay, so here we're gonna need numpy dot exp for the exponential. Okay, so we've got that, and then we need to do the division. So this is the bottom part, so it's 2 times variances, or IDX. So remember, it's 4. And this is, so that's going to be this part here. So 2 times the variances in the denominator. And then in the numerator, it's got to be x minus mean squared, right? So this part here. So go back to the code and just do that one. So that's going to be xs, which is our sample in question that we're comparing, a vector of size 4, minus means IDX, which is basically, for that class, is the mean vector. So we take the sample xs of size 4 minus the vector the means vector for that class of also of size 4. Okay, and so that's the difference. And then this has to be done squared. So that, let's add another parenthesis in here. Because we're going to square it. So let's do. Give me a second. I think I messed up the parentheses. I think the denominator is correct. So here, yeah, I want to add 1. Oh, it keeps, that's what it's doing. It's deleting it. And then when I do that, that's squaring it basically. So that's x to the 2 or whatever. So I'm squaring the difference. So xs minus means squared. And then I think my equation was missing a -1, so just throw that in there. All right, so that's actually the Gaussian function. So if I save it, again, let's go over here to the, we're doing this equation, except remember that we're doing it on a vector basis because the vectors are of size 4, okay, not of size 1. So that's the only little trick. All right, so that should be the Gaussian function. So now, given a new sample, we can run it through all the parameters, divide the numerator by denominator, and it'll give us a probability, indicating if that sample basically belongs to that distribution or not. And if you remember, the intuition with that was something like this. So the intuition was, I have determined that this is the distribution of class 1, right? C1, I've got the mean, standard deviations or variances, and then now I'm going to throw in that X. So let's say sample 1. For this particular class, sample 1 will have a probability of, let's say, 0.20 of being in that group. That's what I get. Then I throw in another one, X2, and I calculate the same thing, the probability, and it's going to be 67. You see it, it's closer. I get another one over here, X3, probability of X3, 0.05. Do you see what we're getting? That's the logic basically. Okay. And so only these are 4-dimensional points. And so there's only that little issue. So now if we go back to the code, okay, we've got the Gaussian. Now we can call it from the predict function. Okay, so I'm gonna do here the predict function. I'm going to create a new list, return per class. And that's my list. So now I'm going to do the same thing. So for IDX and class in enumerate, this is exactly what we did during training. List of classes. So I need to compute all the probabilities per class. So IDXC, calculate all of them and select the most likely. So for IDXC and enumerate list of classes. Okay. And if you think that's now this step, this is what we're about to do. Okay, we need to do it for every single one. So for C1, for C2, for C3. So we need the the priors, right, and the likelihoods. Okay, so we need this, and we need them for every feature basically. Okay, so I'm going to go ahead. I'm going to go here. And I'm going to say, so I need so I'm going to collect and list and oh, this should be result. So I'm going to collect in result per class each probability. So for class 1, for class 2, class 3, and then I'm just going to select the highest one. So what I want to do, the last thing I want to do is, once I process the data, I have a probability. So I'm going to do a return per class, or sorry, I keep saying result per class. So result per class dot append probability per class. Okay, so you're just adding these. So, and then once you have, you're going to have 2 basically for this problem. If you had 3 classes, you would have 3 probabilities per class, right? And then once you have that, you just pick the highest one. So in this case, you would pick here, you would use a function called np.argmax, and from here then, from the probabilities result per class, okay, we would pick the highest one. So np argmax. This will just pick the class, the probability that's the highest of the two. So we have two probabilities, and it'll pick the second one. So that's the second class, and that's what gets assigned. So and we'll do this function np argmax. Okay. From yeah. Oh, I did this twice. I think I meant... No, what I meant is here. Sorry, I meant array. We're just gonna make this into a. This is a list. We're gonna make it into a NumPy array. Okay. So this is just more of a like a mechanical thing to take the results per class list and convert it into a NumPy array. Once this is a NumPy array, then we can calculate the np argmax. Okay, and then we're going to use that value. All right, but now then I need to calculate this value probability per class. So I need to figure that out. Okay, so I'm going to do probability per class, and I need to figure out what that's going to be. Right, so probability per class actually needs to be the sum of the prior or priori and the other ones. Let's call it posterior. All right, so what's happening there is we're actually summing so this function here, where we do the multiplication, this is the priori, the last one, right? And these are the posteriors. But remember what I had said, that multiplying them does not work very well. So we have to instead add them. So if we go to, here, we had said yeah, here it is. So we had said that the multiplication of all the values actually works better as a sum of logs. Okay, so that's the thing that's happening there. We are actually implementing the function of multiplying each probability, right? But instead, we're just going to log them and add them. Okay. Remember, this is feature 1, feature 2, feature 3, feature 4, right? And they would get multiplied. That's the equation that we have here. This equation, remember? This equation is probability of x1 times probability of x2, probability of x3, x4, and then the last PC. But instead of multiplying them, we do the logs. So that's really what needs to be implemented here. So we're going to go back to here, I think. Going to go back to the Jupyter. And we're almost done, actually. We just need to do this part. Okay. So here then, these two parameters are that. So we need to accumulate them. So we're going to need prior, and we need also posterior. Right? So we need those two. So the prior will just be the priori, which had the class, right? So I'm going to take then priori like that of the particular class IDX. Because remember, we got that from here, right? So we discussed how to get that from here. That's the value. Remember, is the number of samples in the class divided by the total number of samples. So here I just take this priori, and I'm going to do NP log on it. So I can change a multiplication into a sum of logs. Good. So that's the last term, okay? And then the posterior is the calculation of the probabilities using the Gaussian. So we just defined the Gaussian here, right? So now we just call this function here, okay? So it'll take our IDX, it'll take our, this XS needs to be X1 sample, okay? And it'll tell us if that sample belongs in that distribution, okay? That's basically it. So we pass the means, and it'll return a vector of 4. So that's the only thing that's you have to remember. Four probabilities, one for each feature of XS, right? So now that we have that, then we can just log. So we can just log, we'll do posterior equal, and then now we need to, because we can't multiply them, we need to log them and sum them. So then we're going to do NP log of the original posterior, right? So now they are logged, all 4 of them for each feature, all 4 features. So now I'm going to do NP sum. And so I add them, and then that result, I just add to the final prior, and that's it. Okay, so another way of thinking about this is like this, right? So let me work this through again in the here. So the way that this is working is we calculate the class probability. What's the, how many samples in class 1? There are 3 samples and there's a total of 6, so it's 0.5. And then that was the prior. And then all I did is I took that 0.5 and I did log on it. And I will add this as my last term. So log of 0.5, that's done. But I still need to do the probability of F1 log plus log probability of F2 plus log probability of F3 plus log probability of F4. You guys see that? That was the same as we had said before in the equation. Probability of F1 times probability of F2 times probability of F3 times probability of F4 times the last part, the prior, which would be that log 0.5, which just comes from the number of times we see samples for that class in the data set. But we don't do the multiplications, we do the sums, right? Now remember, these probabilities come from looking at that sample and seeing if it belongs to that distribution. So for X1, we want to know if XS, the value of it, falls within that distribution. And we get these 4 probabilities. So that's what we have in that piece of code, right? So in that piece of code, here, we run the Gaussian function, this one, and it returns a vector of 4 posteriors and then we just log each individual one and sum them. So it's almost like we take the vector that was returned here, right? So we get a vector, let's say like this, from that Gaussian function. Let's say, 0.3, 0.5, 0.1, 0.4. We're going to log each individual one separately, and then we do sum. So we just sum them. And that's equivalent to this, and it does it. Okay, so you can always have, you could have written this more elaborately, or more specifically to this, but then it wouldn't work for other things. So the code that we have here at least works for everything. All right, and so that's it. So as you can see, we get that prior probability first, then we run our X data through the Gaussian, get the posteriors for 4, then we log each individual one and sum all 4 into 1, and that sum posterior is just added to prior, and then we have our probabilities get added. Okay, so now we have this complete, and we just need to do the last part where we return the class that we want. So out of the class that we have, which is list of classes, this is going to give us np-argmax will give us the index of the highest value. So we have a list of classes 0 and 1. This will tell us which class to select. So it'll give us the index either 1 or 0, and that's it. Okay, and that should complete the problem. So as I said, play with the code. That's really what I would say. Print everything, print statement. I really just want you to understand the logic of naive Bayes. Obviously, I wouldn't ask you to implement this from scratch. The beauty about this is that if you understand this code, naive Bayes, you understand everything else that's probabilistic in nature, right? This is a very complete view of it. Okay, and usually, as you have seen, you can just use sklearn or Weka to calculate naive Bayes. You've been using it all semester, but hopefully now you have a sense of how naive Bayes works. So now, unless I have any typos here, I think we can run the code now, and hopefully it'll work. So let's go ahead and run that. Okay, there's an error. Where is the error? I may have a typo here. In the for loop of train. This one? Well, that should be the function name though. So that's a function. So... Oh, var, yes. Yeah, good catch. I see what you were saying. Not mean, but var. Yep. Okay, and so let's try it again. Oh, there we go. So, and that's it, right? So the code now, produces results. And you guys can calculate the accuracy, right? Because it was even a question on the exam, right? And you guys, all of you answered correctly. So you can just use that same function or the sklearn function to calculate the accuracy. Just by looking at it, what would you say the accuracy is? Does it look very accurate? Somewhat accurate, right? What did we say about naive Bayes? It's not the most accurate, yeah, but it's the fastest, exactly. So And there it is, right? So at the end of the day, my goal is for you to kind of understand the three types of machine learning that you usually encounter. So here you can see again the vector space ones, which they can all be vector space, but the distance metric approaches is what I should say. The probabilistic approaches, which is what we discussed today, and next week we'll discuss hidden Markov models, which build on top of this. And then finally, the thing that you're probably most interested in and where you're going to find the most power, and that's why we'll dedicate, almost the second half of the semester, will be the, after spring break, neural networks, okay? Which neural networks, you'll see they're a little bit different, but in terms of parameters, you have to learn a specific set of weights. Whereas here you've learned that, what did you learn? What are the, so if I asked you on the exam, for instance, what are the parameters that you have to learn for probabilistic methods to be able to make predictions? What would you say? Right? The means and the variances, right? Because the Euclidean distance gives you the probabilities. At the end of the day, it's kind of a already well-defined model, right? So go over here. The model, like, sorry, it takes me a long time to get this. Yeah, so the model basically is always like this. This probabilities don't change, right? But the parameters that you have to learn are this prior, by how many samples belong to that class, and then these probabilities, right? And these probabilities, as we said, okay, so I have to go to the other one. Those probabilities come from this equation, right? We have to learn the means and the variances. Okay? So those are the parameters for these probabilistic methods. Okay, the equation is not a parameter. The equation is just, that's the equation, right? It's the things that, this is the input, and the mean and the variance represent the data. It's like, I've looked at the data. So it's almost like I'm saying, again, height, right? So I look at you guys, and the mean and the standard deviation for your heights is, let's say, 5'11", right? And so then now a new sample comes in, and you want to say, is that similar for this class, right? Because there could be another class over there, and that class, they're all taller. Like the mean for them is what, 6'2". So if you bring one person and that person is 5'9", right, then you compare it to this class, well, the mean for height, and that's just looking at one variable, not all of them, right? But if the mean of just one height is 5'9", no, the mean is 5'11", and that person is 5'9", that person goes to the other class, the other group, right? And the mean for them is 6'2", and that person is 5'9". Which class does that person belong to? Just by looking at that one feature. This one, exactly. Do you see that? That's the intuition with this. It's not that much of a stretch. The code is convoluted sometimes because of these Euclidean, this Gaussian, but that uses means and variances and all that. But the idea is pretty straightforward. All right, that's basically it for me. We've concluded naive Bayes. You've got the code working. I'm not going to assign a homework for this, given that the code runs. So this code runs, Weka runs, right? Also, naive Bayes is not necessarily the greatest, but it's good foundational to understand probabilistic. So no homework, but you do have the singular value decomposition recommender system. How is that going? And I'm going to stop the recording. Have you guys started working on that?